Hello everyone. This unit is introduction to DSP processor. Okay, so just for revision purpose, I would like to give a small uh, a view on what is the DSP processors and how it is going to work in real-time applications. Okay, so before going to start, first of all, what is the meaning of processor? Okay, so a processor, or we can say a microprocessor, is a small chip which is placed or which is resided inside of a computer device or any electronic device, and by taking inputs from the input devices and performing some processing in terms of by using arithmetic and logical units, okay, and perform some process and finally which gives the output, and that is a basic general definition for microprocessor. But whereas this unit is completely deals with this programmable DSP. That is, this is also one type of microprocessor, but which is programmable and which is completely different from the conventional microprocessor. So this programmable DSP, which is mainly designed with specific significance, and the significance is nothing but it is mainly this processor is mainly useful for digital signal processing applications. For digital signal processing applications. Okay, so this one. But whereas in conventional microprocessor, so it is a general purpose applications. It is mainly used for general purpose applications. So it is not useful for the digital signal processing applications. But what about maybe there are some sort of advanced microprocessors are there, a reduced instruction set of computers process also there. These processes which are used to which are somehow it can perform digital signal processing applications, but these microprocessors, advanced microprocessors and RISC processors, they are not reached up to the mark for processing of digital signal applications, even though they are also performing digital signal applications, digital signal processing applications, but they are not reached up to the mark. Okay, so that is a one issue. Or if you're talking about in terms of low power requirements or cost, see, low power requirements, cost, and real-time input-output capabilities, and speed in terms of on-chip memories. So these programmable DSPs have an additional advantage over the compared to the advanced microprocessors and RISC processors. So this unit 6 in this main unit 6 is completely deals with this, how this programmable digital signal processors they are worked, they are going to work in how they are uh, perform digital signal processing applications. Okay, so we will discuss one by one. Multiplier and multiplier accumulator is one of the common operation in the process of digital signal processing application, and which is done by the programmable digital signal processor. Okay, so here this multiplier and multiplier accumulator is the one of the most common operator. Okay, so which is required in digital signal application, and that too it is performed an array multiplication. Okay, so to perform this the array multiplication, which can be done by using a single multiplier and an adder. You will see the single multiplier and adder here. So this is a multiplier. This one is the multiplier, and this one is the accumulator or adder, which performs the accumulator adder performs. So here with this from this figure, so you will see, so we are applying input data here, and this is a impulse samples response, and this is an array. Okay, now we will see how this is going to work. Okay, so here before the next sample of the input signal array at the input of the array multiplication should be completed. What does it mean here? So whenever, see here the number of samples, see we are applying input here, we are applying in sample by sample. So already the sample impulse and sample response is already existed there. Okay, so whenever the samples are applied at this portion here. Okay, so before the next sample of the input signal arrays, what happens here? The input at the input of array, already the previous samples already existed now. So those previous samples, the array multiplication should be completed. Okay, let us consider now. See, so to obtain the response for yn. Okay, so the x of n, initially it requires an x of n sample and h sample response. Okay, so this x of n array samples which is multiplied with this impulse response samples, and the result will be stored in accumulator, and it will be stored in register. Similarly, if you obtain fn y of n plus 1, okay, so which requires the x of n plus 1, sample. So if you want to produce the x of n plus 1 sample array, what should be done? So the previous sample should shift it to right side one position, okay, and the new sample should insert here. Okay, so after that the new sample is inserted here. This x of n plus 1 sample, which is this the vector or the array of this x of n plus 1 samples, which are multiplied with this again the impulse response h, and again which is multiplied here, and the accumulator, the adder result will be stored in register like this way. So before the next sample at the input signal arrives at the input of the array multiplication should be completed. Okay, so in this process it requires, so two process at a time. One is multiplication and as well as accumulation. Okay, so if you want to uh, utilize this programmable DSP, so which requires these two component hardware elements, one is the multiplier and another one is a accumulator. Okay, so here uh, there are two types of approaches are there for this producing of this hardware elements. Okay, one of the first approach is a dedicated mac unit is nothing but multiplier and accumulator unit. Okay, so if you want to produce a dedicated mac unit, and which is implemented and in hardware, so which integrates the multiplier and accumulator in a single hardware unit. So this is the first approach. So this one is the first approach. Okay, and second approach, what is the second approach? So in the second approach, so you can utilize two different hardware elements. One is multiplier and accumulator separately. So you can use one single dedicated mac unit, or either you can use one multiplier and accumulator, two different circuits. Okay, so separate. Whatever it may be, the most important thing is that either you will choose any one of the approach. Okay, so the mac operation which can be completed in one clock cycle only. This is the most important point. Okay, so here to perform this array multiplication, so here this array multiplication is nothing but which is perform a mac operation. Okay, so to perform this mac operation, so the circuit requires the number of clock cycles are 1. That is the thing. Okay, so here the presence of this hardware multiplier and multiplier accumulator is one of the mandatory requirements of programmable DSP. See, this is one. Okay, so why it is required? To process the digital signal processing applications. So this MAC operation, this multiplier and multiplier accumulator, is one of the mandatory requirement for programmable DSP. Okay, so this is about the multiplier and multiplier accumulator. Okay, and next see, so here in this figure what you observe here, for each and every new sample arrives at the input data, the previous samples should shifted the array samples should be shifted to uh, right side by one position. Okay, so instead of doing like this, okay, so there is a possibility is there, that is that so here instead of shifting the elements of action samples to right all at a time after finishing the vector multiplication, so we can approach another method. That method is nothing but by shifting a separate single samples. So each of the elements we can be shifted separately as soon as of the multiple and accumulator operation that can be performed uh, is completion over. Okay, so this can be done by using the instruction MACD instruction. Okay, so here what I want to express here. So instead of shifting the elements of the xn array towards right all at a time after finishing the vector multiplication, you can send each of the element may be shifted separately as soon as the MAC operation is completed. The MAC operation is going to be completed. So this can be done by using the programmable DSP. Okay, it utilizes one instruction, one special instruction called MACD. MACD means multiply accumulate with data shift. Multiply accumulate with data shift. So with this multiply and accumulator with data shifter, okay, so which can perform multiplier and as well as accumulator operation by simply shifting the data by one, one bit by one position. Okay, so here I'm going to explain this instruction with the help of example here also. By using this instruction, by using the instruction MACD, either programmable memory or DMA memory, data memory. So PMA means programmable memory and DMA means data memory. So which multiplies the contents of program memory with the contents of data memory with the address of data memory and stores the resultant product register. See, as we discussed earlier, so here in this diagram, if we just replace with input data with program memory, and this impulse response is the replaced with data memory, so you can understood the example very clearly. See here, I think you can understood the concept very clearly. Okay, so here and the contents of program memory with contents of the data memory with address data memory and stores the result in a product register. Okay, so like this way in programmable DSP, so which is performing multiplier and multiplier accumulator operation, especially in array multiplication by using this MAC operation circuit. Okay, so this is the operation of multiplier and multiplier accumulator. Okay, the next topic is modified bus structure and a memory access scheme in programmable DSPs, digital signal processors. Okay, so from the previous topic we learned about the multiplier and multiplier accumulator operation and the importance of multiplier accumulator operation with data shift or data move operation. Now in this topic we are moved a little bit further by using modified bus structure and memory access schemes in programmable DSPs. So in this modified bus structure and memory access schemes, we mainly use the instruction like MAC operation with data move. The instruction named as MAC operation. So that is multiplier and accumulator operation with data move instruction. So if you want to perform this MAC operation, MACD instruction, this MAC operation with data move requires 4 memory access per instruction cycle. 4 memory access per instruction cycle. Okay, now we will discuss these 4 memory access per instruction cycles. Okay, what is the first one? The first one is the fetch the MAC multiplier and accumulator with the data move instruction from program memory. Similarly, second one is the fetch one of the operands from the program memory. Third one, fetch the second operand from the data memory. Fourth one, write the contents of the data memory with address of data memory into the location with the address of data memory plus one next location. That is next location. Okay. See here, it is accessing 4 memory access per instruction cycle. So first instruction, what is that? Which fetch the MAC instruction with the program memory. Second one is fetch one of the operands from the program memory. Third one is the fetch the second operand from the data memory. And third one, write the contents of the data memory with the address data memory into the location with the next address location of data memory. Okay, see, uh, literally by combining, if you observe all these 4 points, okay, if you see according to this these four instructions, and you will see you can observe in this diagram. Okay, so here the input data which is nothing but this data are always stored in data memory. That means the input samples, so which is used to store in data memory. Whereas in the impulse response which is used to store in program memory, which is used to store in program memory. Okay, so here the MAC operation, from this MAC operation, the input data which is always stored in on which memory? Data memory. And the impulse response. So this impulse samples response which is used to store in always in program memory. Okay, so the MAC operation, this MACD instruction, which is can be executed in two types of architecture. One is Van Neumann architecture, and another one is Harvard architecture. Now we will see according to the type of the MACD instruction based on the architecture, based on the type of architecture, the MACD instruction will take takes the will consume the number of instruction per cycle. Okay, first of all, what is the Van Neumann architecture and Harvard architecture? Okay, so in Van Neumann architecture, in this architecture, it is consisting the processing unit. It is consisting, say, then processing unit is there. Okay, processing unit is there, and control unit is there. Okay, but it is consisting one single memory, that is data and program memory only. It is consisting one single data and program, one single memory only. Whereas coming to the Harvard architecture, okay, unlike it consists in two types of memories. One is a data memory, another one is program memory. See, once again I explain. In Van Neumann architecture, it is consisting one single memory only. That memory is consisting of both the data and program. Okay, but here in Harvard architecture, uh, it is not like that in Van Neumann architecture. In Harvard architecture, it is consisting two separate memories. So one memory is allocated for data memory, and another one is allocated for program memory. Okay, so based on the structure, based on the architecture, that model of architecture, now the MACD instruction is executed. Okay, now we will see in Van Neumann architecture, the MACD instruction which is executed, okay, in such a way, so which requires four clock cycles. Why? What is the reason? The reason is that it is consisting of only one single memory only. That memory is consisting on data and as well as a program. Okay, so because of this Van Neumann architecture, okay, so this architecture requires a single address bus and as well as a single data bus. A single address bus and as well as a single data bus. For what purpose? For accessing the program as well as the data memory area. Okay, so it requires two types of buses. One is single address bus and as well as a single data bus. For what the purpose of to access the program and as well as a data memory area. Okay, so this is in Van Neumann architecture. So because it utilizing two buses, one is a single address bus, another one is a single data bus. Okay, so it requires how many clock cycles? Four clock cycles. Okay, so we can reduce this number of clock cycles. We can reduce the number of clock cycles. Okay, so there is an alternate method is there. Okay, and what is the alternate method is that so instead of using two buses, we can use one single data bus. It can be utilized for both address and data. The bus which is used to carry the address and as well as data. See, this is from this data bus. So with this the data bus we can okay. So the data bus which is used to carry both address and as well as data. Okay, so that is happening in MACD instruction. So by using one single uh, bus, the bus is carrying both address and single data information. Okay, so in order to reduce the number of clock cycles requirement. Okay, while coming to the Harvard architecture, So already we discussed this hardware architecture consisting of two separate buses for the program and data memory. Why? Because it is maintaining two types of memories. One is program memory. It is specially allocated one memory for program and one memory for data. Okay, so the contents of the program and data memory can be accessed in parallel. This is very quite interesting factor in hardware architecture because of it is maintaining two different types of memories. So and it is consisting two different buses. So one bus is allocated for data memory and another bus is allocated for program memory. So the contents of the program memory and data memory can be accessed in parallel. Okay, so when the operand is executed, if we want to fed the memory from data memory to the processing unit, then only one instruction code can be is required for the from the program memory to the control unit. Okay, whereas the processing unit consisting of registers. See, in this processing unit, what is processing unit is consisting of? It is consisting of registers and the processing elements like multiplier accumulates and multipliers, ALUs, shift registers, like that. Okay, so this is the processing unit. So that is the basic advantage of hardware architecture. Okay, so because with this hardware architecture it can maintain so it can perform the execution, the accessing of the program memory and data memory simultaneously. So most of the programmable DSPs they are utilizing this hardware architecture only. They are following the hardware architecture. Okay, but with little modifications there. So this is the actual hardware architecture, and this is modified architecture. So the programmable DSPs follows the modified hardware architecture. Okay, so what is the difference between this hardware architecture and modified hardware architecture? Okay, let us see in this modified hardware architecture. Okay, it is also consisting two buses, just like a hardware architecture. Okay, but there is a little difference there. Okay, one set of buses which is completely which is used to access a memory and which has both program and data, whereas in another bus is there now. So the particular bus which is used for only data memory only. Okay, so the data can be transferred from one memory to another location. So this is a quite a small little difference between hardware architecture and modified hardware architecture. So based on because of this additional advantage is there, so the programmable DSPs will always follows the modified hardware architecture. Modified hardware architecture. Okay, so with the hardware architecture, the number of access per clock cycles was also okay is clearly to be shown by two only. Why? Because it requires two buses, it consisting of two buses, so the number of access per clock cycles is also reduced to two. Okay, so if number of clock cycles are reduced, so that means the speed performance also is increases. That is quite interesting. Okay, and if you want to increase the number of access per clock cycle, you can add another bus is also. You can add another bus. Okay, for example, if you want to use three separate address and data buses, so which requires the number of memory access clock cycles can be increased to three, but if you want to increase the number of address bus data buses, what happens? The cost of IC also increases. Why? Because and if you want to add more number of buses in that IC, which causes to increase the more number of pins, and which leads to increase the area of the IC. So obviously what happens, the cost of IC is also is going to be increases. Okay, so instead of using more number of buses in hardware architecture, the programmable DSPs use multiple buses only for connecting the on-chip memory to the um, control unit and data paths. See here. So the programmable DSPs are the multiple buses for connecting the on-chip memory to the control unit and data path. Okay. For accessing off-chip memory, it uses only single bus. Off-chip memory means here there is a dedicated bus is there now, which is used to access only data memory. Okay, so if you want to access the off-chip memory, that means data memory. Okay, it is dedicated for only single bus and which is used for accessing both program memory and data memory also. Okay, so because of this reason, any operation that involves an off-chip memory, which is very slow compared to the using on-chip memory, which is compared to the using on-chip memory. So that is a thing exists in modified bus structure and memory access address in programmable DSPs. Okay, and next we will see multiple access memories. Okay, so just now we discussed that. Okay, so if you want in programmable DSPs, if we can use more number of buses. Okay, so what happens here, for example, if you see if you can use a separate address and data bus, what happens, the number of memory access clock cycles can be increased to 3. Okay, but instead of using multiple buses, okay, for connecting the on-chip memory to the control unit and data path, okay, we are going to reduce the number of clock cycles by 2. Okay, so here uh, the number of memory access per clock period can also be increased by using a high-speed memory that permits more than one memory access per clock period. Okay, see here also given one example, that is a dual access RAM, DRAM, that means a dual access RAM, which permits two memory access per clock period. Okay, so multiple access RAM may be connected to the processing unit of the programmable DSP by using the hardware architecture. For example, this DRAM connected to the programmable DSP with two independent data and address bus, which can be used to achieve four memory access per clock period. So either we can provide multiple buses or we can use multiple access memory, whatever it may be. So if you want to use multiple buses or multiple access memory, okay, ultimately the program DSP, okay, so it can the the programmable DSP which can be perform the multiplayer and accumulator operation very effectively. Okay. See, the another part is that multi-ported memory. See, already we discussed in multiple buses and multiple access memory. Now we are going to discuss about multi-ported memory. Okay. So one of the most important technique adapted by increasing the number of clock periods, which is used to multi-ported memory. Okay. See, from this diagram, this is a dual port memory. This is dual port memory. If you can observe, so this dual port memory, which is consisting of two independent data buses and two independent address buses. Okay, so these two independent data buses and two independent address buses, which are used to access the memory access, which can be achieved in a single clock period. Okay, so multi-ported memories which distributes the need for the storing the program and data in two different memory chips. Okay, in order to permit simultaneous access to the both program and data memory, program and data memory. But with this uh, multi-ported memory, okay, there are some limitations also there. Okay, now I will see the limitations. One of the major limitation of this dual ported memory is its cost is increases. So this is very important. Okay, as compared to the two single ported memory. So even though it is maintaining two independent data buses and two independent address buses, okay. So with this technique, what happens? The cost is as increases as compared to the two single port memories. Okay, and if the cost is increases because of the large number of pins and larger chip area is required for dual port memory, larger number of input pins requires a larger and more expensive packets and a larger die. So the cost of increases means it is due to the number of pins increases. And if number of pins are increases, the area is also the area of the drill part is also increases. Okay. So because of that reason, so it is considered as one of the limitation for dual port memory. Okay. Now we will see the applications. Okay. Now applications in some programmable DSPs combine the modified hardware architecture with the dual port memories. Okay, so the best example device is a programmable DSP device, which is consisting of modified hardware architecture and dual port memories, Motorola DSP 561XS processor. So they have a single ported program memory and a dual ported data memory. Okay, so in this one program memory access and two data memory access can be achieved per clock period, per a single clock period. Okay, so these are the applications of multiplier and accumulator, and multiplier accumulator with the data shift operation, and multiplier accumulator by with the help of multiple access memory, dual port memory, and as well as multiple buses. Okay, so the next one is VLIW architecture. That means VLIW means very long instruction word. very long instruction word architecture. Okay, so in previous programmable DSPs, it follows Harvard architecture, that is modified architecture. Now we will see the another type of architecture which is followed by the again programmable DSPs, and the type of architecture is nothing but very long instruction word architecture, VLW architecture. Okay, so let us see how this VLW architecture working for programmable DSPs. So these programmable DSPs, which is having a number of processing units such as ALUs, multiplier accumulator units, and the shifters, etc. Okay, and also data paths is also there. And this VLAW is accessed from memory, and which is used to specify the operands and operations to be performed by each of the data paths. Okay, so here the access from the VLI instruction word, which is accessed from memory and which is used to specify the operands and operations which are to be performed by each of the data paths. Okay, and this multiple functional units will share a common multi-port registers files for fetching the operands and for storing the results. Okay, so this is all about the multiplier operation. Okay, and see the other one is a parallel random access by the functional units to the register file, which is facilitated by the read and write crossbar operation. Okay, and the execution of these operands in the function units, which is carried out by the concurrently with the load and store operations of the data between RAM and register file. So everything is existed in this VLAW architecture. See, this is program unit, and this is multi-port register file, and read and write crossbar, functional units, and instruction cache. Okay, so this VLAW instruction cache will issue the instruction to the functional units, and these functional units will execute the instructions according to the read by using read and write crossbar operation files, and this read and write operation, the data will be collected from this multi-port register file. Okay, all are combined together, which forms one architecture. That architecture nothing but VLAW architecture, very long instruction word architecture. Okay, so here see the things. So the one is the access from memory and multiple functional units, and parallel random access mechanism, and execution of the operations and functions. All are performed combined together. Okay, so the performance of that gains, which is depends on the degree of parallelism, the algorithm selected. Okay, and the number of functional units. And but here the number of functional units is one of the drawback for the also VLAW. If the number of functionals are increases, okay, and again the cost of the hardware is also going to be increased. That is one of the limitation for this VLAW architecture. Okay, so and one more thing is that it may not always be possible to have independent stream of data for processing. So this is all about the very long instruction word architecture. Okay, in it is utilized in programmable DSP processor. The next most important concept is pipelining concept. Okay, so one of the best approach which is adapted for increasing the efficiency of the advanced microprocessors and programmable DSP, that is called instruction pipelining. Instruction pipelining. So an instruction cycle start with fetching of instruction and ending with the execution of the instruction. So including the time storage of the results, which can be split into a number of micro instructions. Okay, so especially in pipeline instruction pipeline concept. Okay, so an instruction cycle requires four micro instructions, which can be said to be four phases, which is as follows. See, these are very very important. The first phase is that fetch phase, in which the instruction is fetched from program memory. Second is the decode phase, in which the instruction is decoded. Third one is the memory read phase, in which the operand required for execution of the instruction may be read from the data memory. Fourth one, execution phase, in which the execution as well as storage of the results is either in one of the register or memory is carried out. Okay, so this is the instruction cycle or instruction pipelining concept. So what is the first one? First one is the fetch phase. First one is the fetch phase. Okay, in this phase the instruction is fetched from program memory. This is very very important. Okay, in fetch phase the instruction is fetched from program memory. Okay, second one is decode phase. Okay, in which in this phase the instruction is decoded. In this phase, the instruction is going to be decoded. Okay. Third one, memory read phase. Memory read phase. In this phase, the operands which are required for the execution of the instruction, okay, may be read from the data memory. Okay. See, in first phase, instructions fetched from the program memory, and what is the instruction fetched from the program memory, that is decoded into the decoder phase, second one. Third one is after decoding the instruction in memory read phase, the operand, what are the operands are required for the execution of the instruction, and those operands are read from the data memory. Okay. And what is the final stage? Execution phase. Okay. In which the execution as well as the storage of the results is either in one of the register or memory action is carried out. Okay. So these are the four phases. Okay. By combining these four micro instructions, which is called as instruction pipeline. So with the help of this instruction pipeline, we are in microprocessor saves a lot of a number of clock cycles. Okay, I can explain by following the timing diagram. Okay, see here this picture, here two pictures are there. One is a figure one and figure two. Okay, in figure one, so the process without pipelining concept, and figure 2 describes about the processor with pipeline concepts. Okay, see here, whatever may be, for any execution of any instruction, any processor requires these four phases only: fetch phase and decode phase and memory read phase and execute phase. Okay. So that here, first of all, I'm going to explain about the instruction cycle of the process with no pipelining concept. Okay, see here, let us consider there are three instructions are there. So the first instruction I1 is there. According to uh, the four phases. So in first clock period, okay, the time, the clock period, first clock period. So the instruction one is in a fetching phase. Okay. And second clock period, the instruction one is going to be in decode phase. Okay. And in third clock period, the decode instruction is going to the read phase, memory read phase. So where it collects the data from the memory read. And the fourth clock period, so the final the instruction is going to be executed. Okay. So for a single instruction, it requires four clock periods. Okay. It is not a big problem. Okay. See, after that, for the next instruction, for the next clock period, fifth clock period, okay, after completion of the instruction first one, then it will consider the next instruction I2. Similarly, it is also considers four clock periods. Okay. And finally, at the eighth clock period, this I2 instruction is going to be executed. Okay. So until and unless, okay, the complete execution of the instruction is completely over, then only the next instruction will going to be will is get into executed. Okay, see here. So the instruction, the first instruction is executed. After that, in second instruction is going to executed. After that, at the ninth clock pulse, the I3 instruction is executed. Okay, so here there are three instructions are there. So the number of requirement of clock cycles are 12. Okay, it's not a big problem. Okay, but if the number of instruction cycles are, suppose if 100 instructions are there. Okay, now see, uh, how many number of clock cycles are required to access these 100 instructions. Okay, so which leads to improve the delay, or which leads to reduces the performance of this processor, because this processor which is not supporting pipelining concept. Okay, so this is about the instruction cycle of the process without pipelining. Now we will see the instruction cycle with pipeline concept. Instruction cycle with pipeline concept we will see. Okay, so in this case, so initially at the time of first clock period, at the first clock period, okay, when t is equal to 1, okay, so what is one? The first instruction is going to I1 instructions fetch stage. Okay, so and the next clock period, so the I1 instruction is entering into the decoding phase. Okay, meanwhile the second instruction I2 is in executed by the fetch phase. Okay, this is not happening in without no pipeline concept. Okay, now see here in this second clock period. So after completion of I1 instruction fetch phase, now it is entering into decode phase. So meanwhile, in this phase, the fetch phase is completely ideal. Okay, when it becomes busy after executing the instruction one, then only it will receive the I2 instruction. But whereas in pipelining concept, so when the instruction is entering a decoding phase, so meanwhile the fetch phase will execute the next instruction I2. Similarly, when the time at the time period of clock 3, okay, so here the I1 instruction is entering into the memory read phase. Okay, meanwhile the I2 instruction is entering into the decode phase. Okay, and I3, if there is another instruction is there, the I3 is also there, so that I3 will also executed by the fetch phase. When the clock period is fourth clock pulse, okay, so the I1 instruction is an executed phase. Okay, so the I2 is in read phase and I3 is in decoding phase, and the next instruction is fetched out by the I5. Okay, so by using this with this concept, we are saving the number of clock cycles, and as well as we are improving the efficiency of this process. Okay, so that is the most important uh, for any processor. Okay, so if any instruction cycle of the processor without no pipelining concept means the performance of the processor is very poor, because it consumes more number of clock cycles. So it will the execution time is also it will take more time. It will consume more. It will consume more time. So the delay is also very high. So whereas in the instruction cycles of the processor with the pipeline concept, okay, so the number of clock cycles are very less, okay, and with that, so the number of clock cycles are very less. So with that reason, the delay is also very less, and the speed, the performance, or the efficiency of this process also the processor is very high when compared to the no pipeline concept. Okay, so that is about the pipelining concept. Okay, instruction pipelining concept. Okay, so the next topic is special addressing modes in programmable DSPs. Okay, so in addition to the addressing modes, basically addressing modes can be defined as the way of accessing the instructions are nothing but the addressing modes. Okay, so here the just like this DSP, it is also similar like as a processor. Okay, but it is a specifically designed for only digital signal processing applications. Okay, so it is also accessing some addressing modes such as direct addressing mode, indirect addressing mode, and immediate addressing mode, which are supported by the conventional microprocessors. Okay, apart from this direct and indirect and immediate addressing modes, the programmable DSPs have some special addressing modes, okay, which permits the single word instruction format and thereby speed up the execution by making and effective use of this instruction pipeline. Okay, so there are also special addressing modes such as the cyclic addressing mode is there, and bit reverse addressing mode there, that are specifically designed for DSP applications. Okay, so the cyclic addressing mode, especially it is used for circular convolution purpose, and this bit reverse addressing mode is especially it is used for fast Fourier transform applications, FFT applications. Okay, now we will see the addressing modes of this programmable DSPs. Okay, there are totally 6 types of addressing modes are there. One is the short immediate addressing mode, short direct addressing mode, and memory mapped addressing mode, and indirect addressing mode, bit reverse addressing mode, and circular addressing mode. Okay, so the first one is the short immediate addressing mode. So this type of addressing mode which permits the operand to be specified using a short constant and that forms a part of single word instruction. Okay, the name itself it indicates the short immediate. Short immediate means so the specified instruction which is a very short constant that forms a part of the single word instruction. So the length of the short constant which depends on the instruction type and the programmable DSP. Okay, see there is one example so given here. So for example, in the case of T1 TMC320C phase, it is a processor which is a programmable DSP processor, 8-bit constant, which can be specified as one of the operands in the single word instruction, like for addition, subtraction, and or exclusive or etc. Okay, and now short direct addressing mode. Again, this short directing addressing mode is in this addressing mode, which permits the lower order address of the operand of an instruction to be specified in the single word instruction. Similarly, so if we say, if we consider the same T1 TMC320 DSP processor, so it is considered 16 bits. So the higher order 9 bits of this memory, which is stored in database pointer, and only the lower 7 bits which are specified as a part of the instruction. Okay, that is the one. Okay, so each continuous block of the 128 words, which is referred to as a one page in T1 DSP. Okay, so that is about a short direct addressing mode. Whereas in memory mapped addressing mode. So in the memory mapped addressing mode, the CPU register and the input output register of the programmable DSPs are also accessible as memory locations. And this is achieved by the storing them in either the starting page or final page of the memory space. Okay. So for example, in TMC3205X processor, page 0, which corresponds to the CPU registers and input output registers. Whereas if you were talking about the Motorola DSP560 processor, the last page of the memory space contains the 64 locations, which is used as a memory map for the CPU and input output registers. Okay, so here in the page 0, the CPU registers and input registers, it is used as a memory mapping addressing. Okay, memory mapping registers. But whereas in Motorola, the last page which is used for memory map for the CPU and input output register. Okay, it depends upon the type of processor and as well as the starting page or final page of this one, memory map addressing mode. Okay. Now the fourth one is the indirect addressing mode. Okay, in programmable DSP, this type of addressing mode has a number of options, and this permits an array of data to be processed in programmable DSP to be efficiently fetched and stored. And the address of the operands can be stored in one of the registers called indirect addressing registers. In case of T1 process, the indirect addressing registers are called as auxiliary registers, AR. Okay, any of these registers can be updated when the operand is fetched using these registers are being executed. Okay, so here this is possible of the having an additional ALU in CPU. So which is especially for indirect addressing mode and registers, that is called indirect address registers or auxiliary registers, ARs. Okay, so these auxiliary registers may be incremented or decremented either in step by one or a step specified by content of an offset registers. Okay, so if you are using T1 processors, okay, the offset register which is called as INDX register, or in the terms of program DSPs from analog devices, it is called modifier registers. Okay, so the contents of the indirect addressing registers may also updated by a constant using bit reverse addressing mode. Okay, the fifth one is the bit reverse addressing mode. Especially these bit reversing addressing mode, especially which is used in FFT computation purpose. Okay, so to perform a binary pattern corresponding to a particular decimal numbers, which is obtained by writing the natural binary equivalent of the number in reverse order, so that the MSB of the natural binary number becomes the LSB of the bit reverser and vice versa. Okay, see, as already told you that so it is especially used for fast Fourier transform FFT applications. So we are using this bit reverser type of addressing modes. Okay, and we are circular addressing mode. So in circular addressing mode, if we want to perform circular convolution operation, then we are using the circular type of addressing mode. Okay, so this type of circular mode addressing modes. Okay, so this is all about addressing modes of programmable DSPs. Okay.